Hey guys, welcome back. So today some we're gonna get into some elf related things here. The plan today is an elf parser and an elf loader. The elf parser should not be too bad. There's the elf format or executable linkable format. It's basically just the executable format for Unix environments. It's pretty well defined, which is good for us. So parsing should be a little more straightforward just because everything's pretty well defined. We can find it online. We can find online resources for it. And I'll actually have some of those linked in the description that I used when I'm going through this and when I was researching elves. And yeah, so hopefully we're gonna go through the parsing the elf here pretty quickly. Then after we get through parsing the elf is where things get a little more interesting. So then after that, I want to make an elf loader. And I basically want to replicate, at least on a simple level, like a proof of concept level, of what the operating system already does when it loads, when it loads the binary to be executed on a Unix system. But I want to do it just so that I can execute a binary without having to use a exec-v or something. I can just load it into a process and then jump to its entry point to execute instead of having to run the syscalls. So that's kind of my idea for it. And yeah, I'm going to start off with giving kind of a brief overview of what kind of the format of the elf and how I'm kind of approaching the parsing part of it. And yeah, the elf header basically is going to have the offsets to program table headers and section table headers. Our main focus is going to be on the program table headers, which will point to the text sections and data sections. Basically, the program headers have the offsets to offsets to the code and to the data that is necessary for execution, which is why the main focus for us for the loader is for those program headers. For the parsing part of it, I'm going to parse the section headers as well. But the section headers have basically represent a logical map of the binary, so a linker will use that when compiling, since it has pointers to everything. So the section headers also point to these sections, to these text sections, data sections, to kind of represent as the map. It also has pointing to a string table, which is the string tables for those sections, so like .text and .data. So for our case, at least for the loader, the section headers aren't useful. They're mainly for, like I said, like the linker and also for debugging. So when those symbols are left in the executable, some of those symbols will be there. And we don't really need that. So there's even options to completely strip the elf of the section headers and it can still execute. If we go a little further here and take a look at the actual struct that is being used for the elf header, this is where when you dump the bytes of the elf, you'll kind of see it, but or the main importance that we're gonna have here is that it gives us those offsets for the program and section headers. So it'll give us offsets to basically an array of those headers, and then it tells us how many headers and how much and the size of each of the headers, which they're all the same size in the array. So one size kind of defines all of them. Besides that, the first couple fields are basically more like the magic bytes that it has, which is basically 7F and then ELF and ASCII. So it needs that to even begin loading at the operating system. Has like the architecture, the byte order, ELF versions, the application binary interface, all that. So there's a few different meta version, a few different metadata items at the start of the elf file. These are important for loading because if there's something that's not supported or you're on a different architecture or something, then these elf files can run. And so operating systems will usually check these, check the metadata to make sure that it's even a valid binary to run on the system before loading it, obviously, because it will just crash if it's a different architecture. And then the next structure I want to take a quick look at was the program header. So these are again important because they point to these text and data sections, but they're the individual segments that are necessary for binary to run. So realistically, it kind of has offset to what I mentioned was segments. So they're basically bunches of those data points. It doesn't point to just like the text section or just data section. There's kind of bundled segments, is what they're called. We kind of go through the attributes of the struct. So our main type that we're worried about is PT load, since PT load segments are the segments that need to be loaded in order for the binary to be executed. So those are our main focus now of those PT loads. But either way, they're all going to be parsed for the elf parser. But the PT load is our uh, our main interest when we get to the loader section. But there are other types, and they have their use cases as well. We have the flags, which is just the permissions that that memory segment should have when it's loaded. There's an offset to where the actual data it's pointing to, whether it's code or data section. Virtual addresses, which is where it should be loaded in a process. There's a physical address, which isn't really necessarily used for all systems. There's file size, which is basically the file image size of the segment. And then there's the memory size, which is the memory image size. So the file memory image size could be bigger than the file image size, just because the memory image size also includes uninitialized data, like BSS memory, and that wouldn't be included in the file in the image size since that's not exactly what it's pointing to. So you would have to handle that also when you're loading. And alignment's just the expected alignment for that segment. So here's kind of a quick overview of what we're looking at. So let me get into coding the parser and I will get back to you guys. Alright guys, welcome back. So we finished up doing the elf parser. I plan to do a few more things to this. I mentioned how I kind of wanted to make this into a read elf utility, basically, something like that. But for now, it's just parsing everything and printing all of it. So we start off with everything's pretty simple. I'm basically just reading out. So the as I'd mentioned before, like the structures for an elf are pretty well defined. So these are all defined here. So when we read out the stuff, we know the size of everything. Plus once you read out the elf header, it tells you the size of the section and program headers. So, but reading out the elf header is literally just reading out the size of that struct, because that struct is living in the binary, or that binary data is aligned in that format. So we just read out the struct here, return it. I just read it into the structure. And then I do to check support for it. So it's pretty simple. If we take a look at our header here, the first checks are these. So the elf file always starts off with these. So we go ahead and this is it being ran. So these are the checks. So 75, 45, 4C, 46. So 45, 4C, and 46 is just the ASCII the ASCII representation of elf. So I just go through, check that, make sure it's an elf file. And then I come through here. I am basically, or it's for the support of what I am on currently. So I'm not trying to check for, I'm not doing correct checks here. Like I'm not doing, let me check my current system and see if this elf is what it is or whatever it may be. So I'm basically just hard checking if it fits, if it's what I need. So x64, if it's the correct byte order, little endian, if it's named dx86, the current version I'm using, and then if it's exec. I left rel in there. I'm just doing et exec, but I also check for rel. There's a bunch of other ones I need to check for like final things, but that's basically what the checks are doing. So it's just going through these values. So I know these values are for my system, so I just did that check. We go back over here, elf supported. Now I display the elf header, and that's the elf header you're seeing. See, we displayed it. You saw our display here, and then we go into the program headers. So these ones are basically very similar to how I read the elves, but the only major difference is there are multiple program headers and section headers. So I just made in the elf header at the attribute phnum here, it tells you how, or this tells you how many entries. So it tells you how many program headers. And if we look down here, this shnum tells you how many section headers. So I basically just created arrays with the predefined size, set that into read program header. Read program header and read section header are basically the same, just with the different values, just with the different with the different values, different sizes, different offsets, different entry size or amount of entries. So we can even take a look at the prototype for it. Yeah, so it's pretty much the same. They just take a header, the array, which has the predefined size, since we know from the elf header. The number of entries, which is the number of headers that should be there. The offset of where those headers are within the binary, so that I can read them in. And then the size, the expected size of each header, and all the headers are the same size. So yeah, so all I do is loop through the number of entries, read in from that offset, or based on, or read the size in from that offset, increment the array, and move that offset up so I can get to the next header. And the same exact thing I do for the read section headers. And then I print these out. So yeah, so I kind of want to swap these out, like instead of flags, instead of just the hex value for the flag, to instead do read execute, read write execute. So it's just easier to read. So that's probably an improvement I'll make in the future, maybe in the next video. But for now, I'm going to go on to doing the injector part. So my quick overview plan of what I'm going to do for the injector. So there's a few ways to do it, but just for simplicity, what I'm going to do is I'm just going to fork a child from this process I'm in. Um, I'm just going to fork a child and map memory into there, and then copy those PT load sections, copy the PT load sections into that. And I should be able to, like, realistically, what I would want to do is do it inside of like a target process instead of just my own process, or instead of a fork child process, or maybe just do it within my own process, something like that. But for now, I think this makes it easier, a little more understandable. At least it was for me when it's like a separate thing. I'm doing it in a separate process, and I didn't want to deal with doing the whole target process right now. But I do want to do that in the future. Um, but yeah, I'm gonna load those load the PT load sections into the mmath memory into a child process, and then jump to execution there. So that's kind of the main goal, that I won't have to use exec v or anything. I can just jump and execute, and I will get back to you guys after I finish that up. All right, guys, so I'm back from implementing the loader part. So I just want to kind of briefly go over some of the code here. Coming back to this, kind of what we talked about before I implemented was basically just follow these steps. So I call inject target process, which is going to be the main function, or yeah, pretty much the main function of the loader that calls everything. But basically what it's going to do is what we talked about. So it's going to create the child process, mmap a section in that process for our binary to live in. We're going to load the PT program segments into the memory there, and then jump to that entry point, the entry point that the elf header gives it to us. So if we go back here, here's that function, the one that's called in main. We're going to fork here, check if it fails. And once we're in here, we're in the child process. So the stuff that gets called in here is from the child processes. So we're going to do program section sizes. And all this does is get the sizes that I need sorry, it gets the sizes of the PT load section segments, and I need that so that I can mmap the correct amount of space, the amount of memory when I load them in later. So it's just getting the minimum and the maximum total size of it. And if we come back down here, right, so we get the sizes, and then we're gonna mmap target process. So it's just a simple mmap command. I just do read and write for now, just because it's a little more realistic. Like you wouldn't probably want all the flags on it, but I think there is a way to a flag that basically just says like it's non-accessible memory at the time. So I don't know if that's like, I need to do more research into. It seems like the OS would do something like this to map the stuff in, but I ultimately end up putting the permissions on it that each PT load segment asks for once I load the things in anyway. So mapping private and anonymous is just basically no file backing, and that the changes I make to the region are basically only visible to that process. Null for here because I don't need it's position independent, so I don't have like an address I need this mmap to exist at. And then total size is what we grabbed from up here. So once we get that, we have our mmap memory. So this is going to be the memory that we're going to work off of to load our segments into. These are just so I know the start and end of our mmap section, like address wise. And then we're going to load the PT load sections in. This is basically just looping through all of the program headers. And then if there's a PT load, then we call this function to go ahead and load it. So this is just getting the permissions that are needed, or that each of the PT load sections want. I think I kind of explained this, but the mem size can be larger than the file size. And if it's larger than that, size needs to still be allocated or loaded in, but zeroed out. We're gonna read the files, sorry, read the binary bytes from our file now, and we're gonna read it into base mem, which is the memmapped memory. I'll just go up their memory, and then we are going to offset. That's what this is. Okay, yeah. So we're gonna get the virtual address, subtract it from the minimum virtual address, and that'll give us our offset, which in like the first segment would be basically end up being 0. The file size, which is the total amount of like text data I need to pull out of it, and then mem offset, which is the offset for it, and then this is the mem setting for the BSS that I was talking about. So then the space left, so I push the pointer basically past the file size. So this has already been mapped in or copied in to the buffer basically, and I'm just gonna push it past the size of what I copied it, and then mem set the rest of the size that I got up here to zeros, and then call mprotect here, and this is what's gonna set the permissions for that space. And yeah, that's basically it. And then it loads the sections in. It goes through all the PT load sections. I think there's like 4 or 5 in the example I'm using right now, which is set this up for the entry call, and then I'm gonna do the entry here. So I get the entry offset, which if we go to main where we called it, let's see where are we at, third one on the elf header. Yeah, so e-entry on elf header is the entry point for that elf, which is where we need to jump to. So mmap mem plus the entry offset minus the minimum v-adder, which again, we're just getting the similar to what we did up here, we're getting an offset. So remember, we don't care about the actual address. So this one I believe will be like 4K some or 40,000 something. Then you get your entry. I just free this struct I allocated and then call entry. Yeah, that's mainly that's a quick overview of the code. But I wanted to do a I ran it for you, or I ran it here, but I wanted to do kind of a GDB walkthrough so you can kind of see the addresses and see the actual things existing in memory, because I think that helps understanding, especially with me and with debugging and stuff. It's always helpful. So we're gonna do this, and I have a few commands. So since we're forking a child, we're gonna need these commands. Make sure that GDB will follow the fork of the child. I'm gonna set these breakpoints. I'll show you where they're at. The 105 and 101. 101 is here, and I basically want to break here so that I can. I'm gonna break here, and then we can take a look at the mappings in memory. So the mmap memory. You can also do it by looking at proc maps. Yeah, I think proc maps. You can check the memory of your processes and stuff. You could do it there also, but GDB also has the info proc mappings, which is basically the same thing that we're going to look at. And then on our next break, we're going to take a look at the entry thing. But let me go ahead and we can go ahead and start the runoff here. Okay. So we hit our first one, and then what I wanted to do, run this. And we have this, so we can kind of take a look at our, we see this is our address, the start of our mmap memory here. So we can take a look at it here, which is right here, right? So it starts here, but it ends at D3000, so ends over here. So it's gonna be like these pages here, and there's multiple pages in map because they have different permissions here, and that's because when I loaded the PT load sections, they have their different. I protected the different sections, so they're split up into pages here. But this is our mmap section here, and this is what we loaded in. This is what we loaded our PT load segments at. So this helps clarify some stuff, looking at the mmap section actually get created and all that. And then we will take a look at actually next one. So our next breakpoint is going to be down here. So yeah. So I did it right before we right before we hit entry, and it's to show at our entry point code that's there. So here's the code that's there. So this is definitely for debugging was helpful. So dump the entry. I think I messed up the entry, like one of the offsets of it. I had some of the addresses wrong, so it would just basically segfault or crash when it jumped to it. And this is a good way to debug that. So when you dump it, if you don't see your code there, then you know something's wrong. We could go through this, but it's basically this. These offsets or these addresses are the BSS and data sections. So we can take a look at that. I think the accumulator, let's find out here. Oh, yeah, accumulator gets set to 0 here. So this is the accumulator. Okay, we can do x/x. Okay, which makes sense, right? Because it's zeroed out right now. But we haven't jumped to the offset yet, or we haven't jumped to the entry point yet, so nothing's happened to it. This should be the counter here, which makes sense also because at this point we're in the loop and gonna add them together, which happens here. And so this will counter, and we could go ahead and dump this all. Okay, so yeah, we can go ahead and dump this as well. Cool. So we see that there's a 3 there, which makes sense since the dot data, there's already the counter variable has already been assigned 3, so that makes sense. Everything looks fine as of now. And then before we break in, or before we jump into entry, we're gonna break here on 6F, which is right one of these. I basically want to break before this because these are setting up the strings. These are hex for the ASCII for this PyLoader test OK string. So I just wanted to do that so that we can dump the area where it's going to get loaded so that we can see those actually strings, those characters actually being put there. So I think that's cool to look at. So we'll go ahead and I think we can that. Okay. So we hit the breakpoint, which is ends up being B3. So it's actually this one. We can do it. And this. So RVP minus 20 is this. And they're being put into RAX minus 20. And it's also in a further down area, but it's going to print out all that space on the stack. So we get our ASCII characters here. I thought that was cool to look at. You can also print it the hex values form. So if you look here, it looks a little different, and that's because it's flipped for little endian. So here it looks different. Yeah, and then if we continue, get the printout here from our syswrite. And these syswrite and sysexit, those are just, they're pretty simple. Like you can just look up for the architecture, like what the syscall would it be, like format, I guess is a word you could use. Like the standard for that syscall for your architecture, and it's basically in the parameters it's going to expect certain values to be passed to it. Okay. I also wanted to show the BSS and data values being changed after. So let me run time. I'm gonna use I wanted to run it again so I could get the addresses again. And we need the break set up again. Okay, we broke here again. We have these addresses. So we're gonna again do this will be got set to 0. So this will be the accumulator. Next address. There we go. 19 here now. And then let's print the counter. Would be 8. So yeah, but that's pretty much sums up the loader. I think it was really cool to set the GDB. So hopefully that was helpful. And kind of understanding where stuff like is literally being placed in memory. It definitely helped me understand it more and help the debugging and everything. Anyways, thank you guys for watching. Yeah, hopefully it's interesting. I'll see you guys on the next one.